Hey there, science fans! Today we're diving into the world of atoms and how they interact. It's all about electronegativity, a fundamental concept in chemistry. Electronegativity is like a chemical tug-of-war. Imagine atoms playing tug-of-war with electrons, those negatively charged particles. Electronegativity measures how strongly an atom attracts electrons towards itself when it bonds with another atom. The higher the electronegativity of an atom, the stronger its pull on those electrons. This tug-of-war for electrons determines the type of chemical bond formed between atoms, whether it's ionic, covalent, or somewhere in between. It's a fundamental concept that helps us understand why different compounds have different properties. Electronegativity is a key player in chemical reactions and the formation of molecules. It helps us understand why some elements are more reactive than others, and why some compounds are more stable than others. So buckle up, because we're about to explore the fascinating world of electronegativity and chemical bonding. Now, what makes some atoms better at this electron tug-of-war than others? Two main factors influence an atom's electronegativity: nuclear charge and atomic radius. Think of it like this: the more protons an atom has in its nucleus, nuclear charge, the stronger its positive charge. This positive charge attracts electrons more strongly. Atomic radius plays a role too. Imagine a magnet and a paperclip. A bigger magnet will attract the paperclip from a farther distance, right? Similarly, a smaller atom, with its electrons closer to the nucleus, exerts a stronger pull on electrons. It's all about proximity. But wait, there's more. Shielding effects also come into play. Electrons in the inner shells of an atom can shield the outer electrons from the full attractive force of the nucleus. More inner electrons mean more shielding, and this shielding effect reduces the effective nuclear charge felt by the outer electrons, impacting the atom's ability to attract bonding electrons. Understanding these factors helps us see why electronegativity varies across the periodic table, setting the stage for different types of chemical bonds. Now, let's take a trip to the periodic table, the chemist's roadmap. As we move across a period, from left to right, electronegativity generally increases. Why? Because atoms get smaller across a period due to increasing nuclear charge, and that means a stronger pull on those electrons. Going down a group, from top to bottom, electronegativity generally decreases. This trend is because atomic radius increases down a group, putting those outer electrons farther away from the nucleus and weakening the attraction. Think of it like a game of tug-of-war again. A smaller, stronger person might have an easier time pulling against a larger, weaker person. Similarly, smaller atoms with higher electronegativity tend to attract electrons more strongly than larger atoms with lower electronegativity. Understanding these trends helps us predict how atoms will interact and what types of bonds they'll form. It's like having a cheat sheet for chemistry. Now, how do we quantify this chemical tug-of-war? We use something called the Pauling electronegativity scale. Developed by the brilliant Linus Pauling, this scale assigns numerical values to elements representing their electronegativity. The electronegativity values range from about 0.7 for cesium, the least electronegative element, to 4.0 for fluorine, the most electronegative element. A larger difference in electronegativity between two atoms indicates a more ionic bond, where one atom essentially steals an electron from the other. A smaller difference in electronegativity, on the other hand, suggests a more covalent bond, where electrons are shared between the atoms. It's like a spectrum, with ionic and covalent bonds at opposite ends and a range of bond types in between. This scale is super useful for predicting the type of bond that will form between two atoms, giving us insights into the properties of the resulting compound. Section 5. Ionic bonding opposites attract, electrons transfer. Let's talk about ionic bonding, the extreme case of the electron tug-of-war. In ionic bonding, one atom wins the tug-of-war outright. This happens when there's a large difference in electronegativity between the two atoms involved. Think of sodium and chlorine. Sodium, a generous soul, has only one electron in its outermost shell. Chlorine, on the other hand, is one electron shy of a full outer shell and really wants to fill it. When sodium and chlorine meet, chlorine, with its higher electronegativity, snatches sodium's outer electron. This electron transfer turns sodium into a positively charged ion and chlorine into a negatively charged ion. These oppositely charged ions attract each other, forming a strong ionic bond. It's like a perfect match made in chemistry. This is how table salt or sodium chloride is formed. Other examples of ionic compounds include magnesium oxide and calcium fluoride. Section 6. Properties of ionic compounds: strong, conductive and brittle. Ionic compounds formed by those strong electrostatic interactions have some pretty unique properties. They tend to have high melting and boiling points because it takes a lot of energy to break those strong ionic bonds. They're also great at conducting electricity when dissolved in water or in their molten state. Why? Because the ions are free to move around and carry an electrical current. It's like a highway for charged particles. But be careful, ionic compounds can be brittle. Their rigid structure means that when a force is applied, the ions of similar charge can end up next to each other, leading to repulsion and causing the crystal to break apart. Think of it like a stack of perfectly arranged magnets. They're strongly held together, but if you shift them slightly, the like poles will repel and the whole structure falls apart. These properties make ionic compounds essential for various applications, from seasoning our food to manufacturing batteries and electronics. Section 7. Metallic bonding, a sea of electrons. Now let's move on to metallic bonding, which is all about sharing, but on a much larger scale. In metallic bonding, the metal atoms pool their valence electrons together, creating a sea of delocalized electrons that flow freely throughout the metal. These delocalized electrons are the key to metals' unique properties. They allow metals to conduct electricity so well because the electrons can easily move throughout the material. It's like a superhighway for electrons. This sea of electrons also contributes to metals' high thermal conductivity, meaning they can transfer heat quickly. Think of a metal spoon in a hot cup of coffee. The handle gets hot fast because of this efficient heat transfer. Metals are also malleable, meaning they can be hammered or pressed into different shapes without breaking. The delocalized electrons act as a glue, allowing the metal ions to slide past each other without disrupting the metallic bond. Lastly, metallic bonding makes metals strong and durable, making them ideal for building structures, tools, and all sorts of things we rely on every day. Section 8. Covalent bonding. Sharing is caring for electrons. Let's move on to covalent bonding, where sharing is caring. Unlike ionic bonding, where electrons are transferred, in covalent bonding, atoms share electrons to achieve a stable electron configuration. Imagine two hydrogen atoms, each with one electron. They both want to achieve the stability of a full outer shell, which for hydrogen means having two electrons. So what do? They share their electrons. This shared pair of electrons creates a covalent bond, holding the two hydrogen atoms together as a hydrogen molecule H2. Covalent bonding isn't limited to just two atoms of the same element. Oxygen, for example, forms a double covalent bond, sharing two pairs of electrons to create an oxygen molecule O2, and nitrogen forms a triple covalent bond, sharing three pairs of electrons in a nitrogen molecule N2. Covalent bonds are the glue that holds atoms together in molecules, forming the basis of organic chemistry and life itself. Section 9. Coordinate covalent bonding, a special case of sharing. Let's talk about a special type of covalent bond called a coordinate covalent bond. In a typical covalent bond, each atom contributes one electron to the shared pair. But in a coordinate covalent bond, one atom donates both electrons to the shared pair. A classic example is the formation of the ammonium ion New Hampshire, 4+. Section 10. Molecular shapes, VCPR theory and predicting geometry. Have you ever wondered why water molecules are bent and not linear? The answer lies in the valence shell electron pair repulsion, or VSEPR theory. Electron pairs around a central atom arrange themselves to minimize repulsion. Think of it like balloons tied together. They spread out to minimize interactions. Similarly, electron pairs repel each other and shape the molecule. Methane, CH4, has a tetrahedral shape with bond angles of 109.5 degrees. Water, H2O, adopts a bent shape with a bond angle of about 104.5 degrees. VSEPR theory helps us predict molecular shapes and their properties.